Hello, I'm Nicholas Dwork, and today I'm going to talk about dichromatic interpolation. This is an image of hyperpolarized pyruvate being injected into the body, and as you can see, it is necessarily low resolution. I'm going to perform the state-of-the-art interpolation on this image. Here it is. And so while it is slightly more pleasant to see this, it's slightly more interesting, there's a lot of detail left to be revealed about the actual structure present in the body. Let's see if we can sharpen this up. Okay, so this is much sharper. How did I accomplish this? Well, I had a trick up my sleeve. I also had an anatomical image available which I could use to sharpen the low resolution imagery. And that's the goal of this project, to combine a low resolution hyperpolarized image with a high resolution anatomical image into a single interpolated image. The first requirement is that the high resolution imagery be the low resolution metabolic imagery when it's degraded. Here, B represents a blur operator and D represents downsampling. I sub M is the high-resolution metabolic image, and M is the low-resolution metabolic image. So what I'm saying here is that the blurred and downsampled high-resolution image should be close to the metabolic image that we actually have. This is an underdetermined linear system. What I'm going to do is add in some information in order to make the problem better conditioned. And what I'm going to say is, make the gradients of the high-resolution metabolic image similar to those of the high-resolution proton image, and only incorporate as much of that as I need to make the image look good. So how is that done? Firstly, we're going to add a second term into our optimization that makes the difference of the gradients small. Note that we don't want the gradients to be similar everywhere. Where the metabolic image is dark, we don't want the gradients to be similar in that region. And so rather than using an L2 norm, we use a weighted L2 norm, where the weights are determined by the linear interpolation of the metabolic image. Okay, so how are all of these ideas combined? They're combined into a single optimization problem like so. I sub m is the optimization variable. An additional constraint is imposed. The metabolic image must be greater than or equal to 0 because we're working with magnitude images here, and they must be less than or equal to 1 because there's a finite number of bits to represent each value of the pixel. This is a convex optimization problem. It can be solved with either the projected subgradient method or with VISTA. So here are the results. On the left is the anatomical proton image, on the right is the low resolution metabolic image. And here's the result of solving for the optimization problem that I just showed you. Here are more results in the heart. Here I'm showing the pyruvate, lactate, and bicarbonate. And here's after the interpolation. Before, after. Once more in the brain, the top row shows several slices of the brain, and then we have the pyruvate, lactate, and bicarbonate images for the corresponding slices. This is before the interpolation, after. Before the interpolation, after. If you're interested in more details, we welcome you to review our preprint available at www.nicholasdwork.com. And thank you for your attention.